Hello everyone, and welcome to a video on the process of linearization. What does that mean? Well, let's do an example and you'll see. So this is kind of based off of one that we've talked about earlier. Peter Popper, in this case, plants some magic beans, some pea plant beans, from his friend Jack. Get it? Magic beans from Jack? Okay, anyway. And these plants grow quite a bit faster than the ones that we talked about in the past. And here's some data. Right? He looks at the time every hour, and here's what the pea plants do in terms of their height. So you can see them growing very quickly. They are magic. So hard to see exactly what's happening even in these perfectly magical beans here in our data table. So let's do a little graph of it using, of course, graphical analysis. There we go. So I'm going to open that up. I'm going to make it big so it fills my whole screen. And you will notice that I've done a little bit of the work already. I've already changed the column headings. Notice time is my independent variable. It's on the x-axis because that's the one we controlled. We decided to take a reading every hour. Height in centimeters is on my vertical axis, which is the dependent variable. And I've typed in the data. And, of course, the points show up on the graph. I've also gone in and changed the title, so it's height versus time, right? Dependent versus independent. Now, when you get a look at this, oh, by the way, remember that if you've forgotten how to do any of that, it's all on the sheet called Data Analysis with Graphical Analysis, which is on the Google Classroom under Lab Help, right? Under the Lab Help topic. It lives there. It's always there for you to use. So, might be a little hard to see here. Hopefully you're looking at this and going, well, that doesn't look exactly linear. Well, let's go down here under the Graph Tools button, bottom left-hand corner. And if I go to Edit Graph Options, one of the things I can do is change the appearance, and I'm going to choose both, so that now I have points and lines. And now you can see that it's connecting the dots with straight lines. But if you get kind of a look at the pattern, does this look like a particular shape you've ever seen before in math class? I hope so. Or at least half of one. Hey, what does this look like? Yeah, it looks like half of a parabola. In fact, we call this a top opening parabola because the opening's up here. Now you might be saying, well, where's the other half? Well, in math class, the other half would be over here in the second quadrant, right? But we don't see that quadrant here in physics because we're not just making graphs of functions. We're dealing with real quantities. And what would a negative time even mean in this case? It doesn't have a physical meaning, so it's not part of the graph that we're looking at, right? So we only get 1/2 of the top opening parabola. But then we have a problem, which is how do we make a predictable math model out of this graph? Well, there's really two ways to do this. One process is called curve fitting, and we could do that inside of this program. Curve fitting would have us basically guess and check what kind of curve do we think this is, use the computer to guess and check if it fits. And that one works. A lot of physics teachers use it. I like to use a process called linearization. In the process of linearization, we're going to try to turn this graph into a linear graph, a straight line graph, that we could then use y equals mx plus b to make a math model out of. Now, how are we going to do that? Well, we're going to take the independent variable. Sometimes we might use the y variable, dependent, but usually we use the independent variable, and we're going to do something to it which will hopefully linearize the graph. Well, what kind of things can we do? There's usually three that we will see most often in nature. There are many different relationships that exist, but there's mainly three that we'll see in our basic mechanics. And that is squaring, square rooting, and inverting. Inverse relationships, 1/, if you will. Okay? So usually one of those three things will linearize the graphs that we'll see. So how are we going to do this? And again, everything that I'm about to show you is also on the Data Analysis with Graphical Analysis page. It's actually on the back side. Right? If this was linear, we'd do a linear fit, we'd be done. Right? But then it says, if your graph's not linear, do what's on the backside. So the first thing we're going to do is we are going to go up here into the data table, and on the 3 dots next to the time column, we're going to click, and we're going down to Add Calculated Column. We're going to create a new column of data doing something to the time, but we don't actually have to go off to the side and recalculate it with a calculator and put it in a data table. We can make the program do this for us. So Add Calculated Column, and it'll open up this little dialog box. First is the name. So this is where we're going to tell it what we're going to do to the time. Now, again, 3 choices that we commonly see: squaring, square rooting, inverting. Which one do you think would be the appropriate one in this case? We can always guess and check and run through all 3 of them until one works, but hopefully you've got enough math background that you might be able to recognize which one, and as we do more of them, right, you'll see them from pattern recognition, I hope, from seeing them in nature. Well, for those of you that understand parabolas enough from math, you might be saying, hey, let's try squaring the time. So I'm going to change the name here to time squared. You make this little caret with the shift 6. Right, so time, shift 6, and then a 2. So that's time squared. My units would be no longer hours. Time is in hours. So time squared would be in hours squared. By the way, there's no fancy way in this program to do like a superscript, right, to make it look really nice. So this is the best we can do in the program. Here we can change decimal places to sig figs. In this point, I'm not going to worry about it, but we could, for example, click this, and it'll now keep 3 sig figs in all of our results. I'm just going to leave that as decimal places. We can even click it to use scientific notation if we wanted. And then here, we're going to insert an expression. Well, you can't just type it in. It's not smart enough to know that. But when you click here, it gives you a bunch of options. There's only so many we can do. Some of them get really complex. There's even some calculus, some logarithms, all sorts of weird things in here. We generally use one of these 2. This is what's called the power function. A and B are coefficients. So this is some number x to the some number. This is an inverse function. Sure, we could make this -1, and that would be an inverse function, but, you know, here's a direct inverse. So since we're going to try to square, I'm going to choose our power function. Once you choose it, it gives you this little dialog thing. This is the coefficient out in front. We never mess with that. We just always leave that a 1. This is what we're going to square in this case. Time, if we wanted to do height, we could choose it there, but we kind of already did that when we worked on the time column. And then we want it to square. Well, if we want it to square, we need to tell it to. Right now, it's just got this raised to the first power. So we need to make it squared. And watch the magic here when we hit apply. Watch the data table. It just made a new column of times squared in hours squared, and it actually squared the times. Little slider down here, see? Took the times and squared them. Now it left 3 decimal places. Right? Again, if we wanted to, let's see, column options, we could go in here and change that to sig figs. Right? Now it's written it to 3 sig figs, and we could leave it that way. Right? Either way, doesn't really matter in this case. So we've now created this column. Now the question is, does squaring the time linearize the graph? Turn this graph into linear? Well, we could do that on this graph, but personally, I like to leave the original graph there because I want to see the way the data looked, originally, and then I want to see hopefully the linearized. Really easy to add a second graph to this. We go up to this box, which is called View Options, and you notice it kind of looks like how the screen's set up. And here is where we can change how many graphs we want to see, or if we want to just see a table, we click on this, it just gives us the table. Right? Graph and table is what it defaults to. But in this case, I want to make 2 graphs. So I click on this, leaves our original graph, adds a second graph. Now you'll notice the table isn't on here. It's just not smart enough. It can't do 2 graphs in a table. If you want to go back to the table, you go back to here and you can choose table or graph and table. Takes you right back. Very easy to switch, right? So 2 graphs. Now I want to do a couple things. First off, notice there's no data points on this second graph because right now it's not graphing anything. right? This one's still graphing height and time. This one's not graphing anything. But let's add a title on. Go down to Graph Tools, right? Edit Graph Options, and we can put a title in here. I want to put in height versus not time, but time squared. I could change the appearance. I could change the scaling, which we don't need to do. I don't really need to do anything but points in this case. So once I do that, get out of there, and notice it's now added a title to the graph. Go down to where, if you want to choose what you're putting on each axis, we go down to the x-axis button and we click on it, and it gives us choices. Well, I don't want time, I don't want height, I want time squared. We go over to the y-axis, do the same thing. Here I want height. So I use the toggle. I don't know why it's a choice down here and a toggle on the vertical axis, but that's the way they do it, right? It's just the way it's programmed. So we toggle the height on. But now notice something. If I get out of there, there's no points. First time I did this with this program, I sat there for a long time trying to figure out why there were no points. And then I realized if you go back here, do you see down here, data set 1, which is the only data set you have? That's turned off. Why does it default to turning your data off? I have no idea, but it does. So when you turn on height, you also have to toggle the data set on. Do you see the points pop on now? So if you forget to do that, right, that's one of the big errors people make when they're using this at the beginning. Like I said, it took me like 5 minutes the first time to figure out, oh, I need to toggle that on too. And so now we have points. Did it work? Did it linearize the data? Well, if we want to check and see, it certainly looks straight, right? We could throw a ruler up there or something. But if I go down to Graph Options and then choose Apply Curve Fit and choose Linear, because that's what we want it to be, and hit Apply, well, that looks pretty darn linear. In fact, these are magic beans, remember, right? These aren't just any beans. These are magic beans. And so you're getting magically perfect data. I can move this up or down so that we can see it all. Look at our results. We get a slope of exactly 10. We get a Y-intercept of exactly 0, which you would never get in real life. We get a correlation coefficient of exactly 1, which means our data is perfectly linear. This means we have successfully linearized the data. We have taken the independent variable on the horizontal axis, typically called x, right? And we have done something to it, in this case squared it, in order to create a linear graph. Again, 3 choices you often see: squaring, square rooting, inverting. There are much more complex ones out there: sine functions, cosine functions, derivatives, calculus, all sorts of things that you can do, right? But we generally focus on those 3 in what we do in here. So everybody clear on that? Again, every step that I did, in the exact order I did them, right, is on the Data Analysis with Graphical Analysis sheet. Right? So use that as a guide when creating your original graph and the other. And this is really what I would love to see, all right, on your when you're doing this yourselves, working in lab. Right? You've got your original graph. You don't need to curve fit it or do anything else to it. Then you've got your linearized graph, successfully linearized graph, with a title and column headings and units, right? And everything's on there. Your linear fit is done, and your data's right there. Okay? All right. Nope, I don't want to save it. So let's keep going. So here we go, right? That's what you just saw. I've just pasted it in here so that we can now work with it. So notice, our second graph is linear, correlation of 1, and it goes through 0, 0. Well, as we've worked with, we know that when you graph 2 variables, and they result in a graph which is both linear and contains 0, 0, that those 2 variables are proportional. But it's not the height and the time that are proportional. That was a top opening parabola. It's the height and the time squared that are proportional. Right? You would read this as the height is proportional to the time squared. So this is a new relationship that we're seeing here, right, in this example. And yeah, I'm doing this with you now because we're going to see it in nature shortly, right? So what does that mean? Well, let's go back and look at our original data. Because these are magic beans, this is perfectly clean data. So it's a little bit easier to see what's going on in the numbers, right? So notice here, if I take twice as much time, if I let the magic beans grow for twice as much time, does the height double? No. The height goes up by 4 times. 2 times the time, 4 times the height. If I take and let the time triple from 1 to 3 hours, does the height triple? No, it goes up by 9 times. 3 times the time, 9 times the height. 4 times the time, 16 times the height. 5 times the time, 25 times the height. You see the pattern? Whatever you do to the time, you have to square it, and that's what happens to the height. That's what it means to have height and time squared. If we let these continue to grow 10 times the time, it would give you 100 times the height. If we only let it grow for half the time, 1/2 squared, we'd only get 1/4 of the height. See how that works? Fun with fractions. Right, so this is a second relationship we are going to see in nature. And there's some questions that are asking you to think proportionally. Right, something we try to do in here. A lot of times concept builders and things like that will ask you proportional questions, right, about things, about relationships that we find in nature. But, that's not as powerful as we can get because it doesn't allow us to make direct predictions. If I let it grow for 5.5 hours, how tall will it be? Right? Or if I let it grow for 15 hours, how tall would it be? Right? For that, we need a math model, right? Rather than just a proportionality statement, a relationship statement. So to do that, we're going to use, again, the linearized graph, and we're going to use our old friend y equals mx plus b. But we're not going to use y and x, or m and b, because this is real stuff. So we're going to put in variables that mean something, and we're going to put in actual quantities for these with units, right, for m and b. So first off, y. Y is what we graph on the vertical axis. We graphed height. So we might use the symbol capital H, like I did up here, right? Lowercase h, capital H, something like that for height. M is, of course, the slope. Now the slope we got right from here, right? We got it from the linear fit. The slope is 10. Units? Well, how do you find a slope? Well, you use the program, right? But how would you find a slope if you were to do it yourselves? You'd do rise over run. So that's where we get the units. The units of rise are centimeters. The units of run, they aren't hours, right? Because that's not this graph that's linearized. They are hours squared. And you could write this as an abbreviation, capital H, HR, something like that, right? I just wrote out the word. It's not that big. So 10 centimeters per hour squared. Those are the units. Okay? Now, I'm not going to ask you what this means, okay, because the interpretation of it's a little bit tough and is really something beyond what we need to know. So in this case, it's not the meaning of the slope that's important, right? It's the actual full-on function that we're going to use. So that's y equals m. Okay? Next step is, what's the x? Well, x is what we graph on the horizontal axis. It's not time. Again, that's not the linearized graph. It's time squared. Don't forget the squared. That's vital in here, right? That's what we graphed to make this linearized graph. And then we need to deal with the y-intercept. Well, the y-intercept is obviously 0, 0. I mean, these were beans, and logically that makes sense. And we actually have a statistical y-intercept of 0, which you would never get in real life. So remember, you would use the 5% rule. You'd take your maximum height, take 5% of that, and compare your y-intercept. But with these magic beans, we got exactly a 0. But logically, what would that mean? Well, yeah, it means that's where it hits the axes. That's what it means in math class. physically, what does it mean to have a 0, 0 point really on both these graphs? Well, it means that when time, or time squared, is 0, what's the height? It's also 0. So when you plant these things at 0 hours, the height of the pea plant is 0 centimeters. Right? That's what it actually physically tells you. And since we're planting beans, right, that makes logical sense. Well, you don't have to add on a 0. So there's our math model. And again, the power of this math model is that you can now make predictions. For any time, you can immediately calculate a height. For any height, you can do a little algebra, and you could solve for a time. A little more algebra than our linear relationships that we've seen so far, right? But it can still be done with just a little more algebra. So you can use this as a predictive tool. But here's one other really cool and important thing about this, okay? Look at this equation. If I gave you this equation and said, make a graph of height versus time from this equation, right? What you would do in math class is you'd pick a bunch of times, 1, 2, 3, 4, 5. You'd plug it in, you'd calculate the height using the equation, and then you'd make a graph. What would that graph look like? Given that this is h equals 10 centimeters per hour squared times time squared. Wouldn't the graph of this equation be that graph? Right? It would be a parabola. So this process of linearization allows us to see the relationship and to kind of prove to ourselves what the relationship is we're seeing in nature, but it also lets us build a math model of both our linearized graph and our original graph. This is the graph that creates this top opening parabola. Hopefully, the next time you see a top opening parabola, you will immediately go, hey, I've seen that before. I know what we should try. Let's square whatever we graphed on the horizontal axis and see if that linearizes it. And if you see a shape that's not a top opening parabola, you might hopefully say to yourself, hey, squaring's not going to work. Let's try something else. But these are kind of skills we're going to build as we continue to do labs in honors physics. So hope you enjoyed this little overview of linearization. And don't forget, when working inside graphical analysis, the sheet data analysis with graphical analysis will tell you how to do everything we did today and before.